This video explains the example of the column for drawing the axial load moment interaction diagram. So the question is to determining the key point A, B, C, D on a section capacity line of the column section shown in the figure. So that is column is for reinforcement. RC column is given 400 millimeter by 600 millimeters, where there is a 1200 millimeter of reinforcement in each face. So there is a compression reinforcement 1200 millimeter square, tensile reinforcement 1200 millimeter square. Bending takes place above the x-axis. FC dash is equal to concrete compressive strength is given 40 megapascals, and yield strength of the reinforcement is given 500 megapascals. Now to start with, we're going to plot A because that is the easiest point. There is no bending moment here. When there is no bending moment here, it's very easy to calculate what happened. Point A, when the load applied particularly from the center of the columns, that was the point A. And then your full columns under the axial compression, the whole surface is point, meaning that everything is squashing down. The whole surface is going to push it down. It's not have any bending. It's just completely, so it has axial shortening in the columns. In that case, we can get the point B. There is no any bending moment in the column. So that is the scenario for axial compression, which is this one, and this is the largest capacity. In the reality, is not possible. Generally, if you have eccentricity in your columns, but this is the highest. This is the efficient way to do it. Is this one. If you have a eccentricity, this eccentricity will increase. That will decrease your capacity of this one. And please note, this is a surface where you can have inside. If your load, design load is within this one, you can have safe. If you falls outside of this surface, you will get this outside of this curve. It will be unsafe region. So that's the very helpful for designing this one. So once you have this axial load moment interaction diagram, you can easily find it out whether the columns falls under safe or unsafe zone. Now first of all, we're going to calculate point A. Now this calculation of the point A with calculation of the squash load, I represented by NUO, and that I just write point A. The Australian standard does not notify point, but just for the explanation I write point A. Now for concrete strength FC dash 40 megapascals, that is given in the questions. 40 megapascals given in the questions. We can find the coefficient alpha 1. I will tell you where we can use this coefficient alpha 1. But if you go to the page number 159 of AS 3600, you can find on clause 10.6.2 squash load, the ultimate strength in the compression without bending. As I mentioned, there is no bending moment, calculated by assuming that uniform concrete compressive stress. So we are calculating the compressive stress alpha 1 FC dash. So alpha 1, you can have this equation, 1 take away 0.03 FC dash, but it should be between 0.72 and 0.85. So if it is less than 0.72, you get 0.72. If you get 0.75, 0.80, you take actual value. If you get more than 0.85, you will take 0.85. So what is this actually, this compression stress? So if you take the columns here with the reinforcement, and if you draw the stress diagram, this actually this is the stress alpha 1 FC dash. Okay, that is the actual concrete stress. So this, how much concrete will going to subjected to stress, that is that stress that we are calculating, getting alpha 1 FC dash. So this alpha 1 FC dash is the stress of the concrete, because you can see that what is this meaning? What is this meaning of 0.72 and 0.85? Why not we just take it 40? Why not we taking 40? Okay, let me calculate first, and then we can discuss this one. So alpha 1 is equal to 1 minus 0.03 FC dash. FC dash, we substitute 40, we get 0.88. Okay, that is not good, because it should be between 0.72 and 0.85. So we take it 0.85. Now my questions here, that we are reducing our so our concrete strength, which is alpha 1 FC dash, that is actually become 0.85 times 40, right? So if I use the calculator for this case, let's say 0.85 times 40, we have 34 megapascals. So that is the concrete strength. So we taking not 40, we taking taking 34. Why is that the Australian standard not allowed to take 40? Because the concrete is made at the site and it has lot of variables. If the same person's making and with the same quantity, when you test it, they will have variations depend on temperatures. If you prepare the concrete in the morning, then if you prepare the concrete on afternoon, it will have a different property. So concrete is very strange materials where its properties are affected by humidity, temperatures. If you are casting the concrete in Sydney, then different than Melbourne or in Queensland or Northern Territory, depending on the weather. So therefore for the uniformity we reduce this one for the safety reason. So that is 0.85, we multiply, we reduce. Some of the cases you can see, if you increase that 0.72, you can go up to, let's say, 28% of reductions. That is maximum reductions, that we go up to 0.28. So now so that's the story about 0.85. So actually we're not taking 40, we're taking 34 megapascals of concrete here. Now we need to calculate the area of the concrete. That's 600 by 400. That's easy calculations. The area of the steel is also 1200 plus 1200, 2400. Now when you have no bending, only just calculating the load, which is your force, which is quite easy, because the concrete will contribute into carrying the load and the steel will also carry the load. How much load it will be carrying? That stress of the concrete times the area of the concrete. So stress, which is we calculated alpha 1 FCDS, which is your 34 megapascals, not 40 megapascals. Australian standard said you can't take 40 megapascals. Actually we need to take this from 34 megapascal, which is alpha 1 we calculated. FCDS given in the question 40. Cross section area of the concrete is given 2400, plus area of the steel is 2400, because we have a compression reinforcement and top tensile reinforcement. So 2400 times the yield strength 500, multiplication gives Newton. We are working everything in Newton millimeters, so it gives you newtons, and it's divided by thousands, give you 9360 kilonewton. So actually we found this one, that first point, the point number A is actually 9360 kilonewton and zero bending moment. So over here, if I just come back here, I can write it down 9360 and zero bending moments here. So that is the point number A, first point that we just found it. Next video we will continue finding the other points using the Australian standard. Thank you.